Hi, my name is Nathan, and the title of my project is Predicting Number of Days on Market, a Real Estate Investors Analysis Tool. And this is the final phase of the project. So, real estate investors consider many factors when investing, and among these factors are generally economic trends, population size, potential cash flow from the property that they usually invest in, and they think about location, and then also average days on market. So for this project, I would be focusing more on average days on market, and this is because if we can estimate average days on market accurately, it helps to estimate holding cost, um, estimate interest on loans, as well as the profitability of the investment that the investor is trying to get into. And so for my objective, I want to find out whether or not population size, income levels, and listed prices predict days on market. And so for my research questions, I have does population size predict days on market? Does household income predict days on market? And does listed price, which is the price, not the actual selling price, but what it was listed for, and in the seasons in which it was listed, does it influence the number of days on market? So for related work, I was able to research and find out that sales price and time on market have a positive relationship. Secondly, I was able to find out that analyzing both sold and unsold property prices can also impact marketing time. Unfortunately, I do not have information on the sold aspect, but hopefully I'll use some of the information I found here to help make a decision on the features I use in the model. And then finally, including a third metric such as location or seller motivation can also impact marketing time. So for the data sources, I use three data sources, one from realtors.com, and then from Census Bureau, I use the annual estimates of resident population and then the median income data. These three data sets were combined using RapidMiner and then SAS to combine, clean, and do everything. And also for the exploratory analysis, everything, and then SAS basically used for the modeling. So here we have a screenshot of the final file, and the final file is aggregated down to seasons of the year, and it has dummy variables for seasons as well as the county for which we would be predicting. These are categorical variables, and since this is a regression, to be able to use them in the regression, we need indicator variables, and so these were also created to help in the model. So here we have our initial exploratory analysis, which shows very interesting patterns here. So as we can see here, the purple bars are telling us that winter time is never the best to sell houses because they stay on the market for long. The best time to sell is this green bars, which represents summer. And so we can see that this pattern exists for 2015, 16, 17, and 18. And so it tells us that this is a very good pattern that we can include in our model. Here also I performed a cluster analysis of population density and days on market in Maryland. And as we can see on this chart, there are four clusters. So we have this cluster, we have this one, this, and this. And then notice that the clusters above population densities that are 700 and above have maximum number of days on market around 130 days. In other words, 3 months, most of the houses in these high density areas sell. However, when we look at the lower density areas, which is this side, notice that maximum is about twice the time it sells in high density areas. So this is, again, this is a very interesting pattern that would be included in the model or considered in the model. And here also we look at the effect of listed prices on days on market. And here too, my expectation was that lower prices would sell quicker than higher prices. But again, as you can see, it's not the case. And here we observe that prices listed between 238,000 to 388,000 sell quicker than prices that are really low, between 88,000 to 238,000. And then another surprising pattern I saw here, as you can see, it occurs across seasons. Down here is the most expensive houses are selling quicker than all the other houses that are priced below that. So that's another pattern we can see down here, but then very surprising what is going on here. But again, this would also be considered in the model. And then next we have the effect of median income on days on market. And here too we see there is a negative relationship between income and then days on market. Our correlation matrix here shows us the correlation coefficients between days on market and all the other variables that are being considered. So here we have days on market and we have all the other variables down on this row. One thing this correlation matrix also does is to help us identify independent variables that are highly correlated. For instance, median listing price and average listing price are highly correlated, so both cannot be used in the model. So we would have to choose one of these, and as you can see here, their correlation coefficient is 0.931. And so this also helps us to identify correct variables that we can use in the model. And so what I did was to test these parameters in the model and identify which ones were best, were highly significant, or increase the performance of the model. So I was able to identify 7 features that I believe were best for this model, and this was based on the literature review we had, based on the patterns that I have walked through, and also the correlation metrics. And here we have the regression model, which is a multiple regression model, as you can see in equation 1. And so we'll be predicting days on market, which is our target variable. So to be able to increase or ensure that the model performs best, I decided to look at the scatter plots for most of the variables that I'm considering, that is the 7 features that I've selected, to find out if any of them has a non-linear component that can be included in the model. So looking at these scatter plots, you observe that they don't really seem like they have any linear relationship. The only one that seemed like that was the population density, and as you can see here, it looks slightly non-linear. However, when I included it in the model, it didn't turn out to be statistically significant, and also it reduced the performance of the model. Here we have the initial model performance metrics for the 7 variables that I showed earlier on. And you can see here that our model is statistically significant, and also our adjusted R squared is about 72%. Now, what I observed was that the target variable was a bit skewed. As you can see on the left here, it is a bit skewed. So I decided to transform it by taking log of it. And on the right, you can see that after taking log of the target variable, it looks more like a normal distribution. And so I decided to rerun the model on the log transformed target variable to see if it would improve the model. And here we can see that again, our model, after running it on the log transformed target variable, is still significant here. And then it increases our adjusted R squared from 72% to 75, about 75%, which is not bad at all. And so, also the parameter estimates, as we can see down here, all the parameter estimates are statistically significant. So hopefully this would be able to predict well in a model. Again, the fact that R squared is 75 does not necessarily mean that it would predict very well until we actually compare our predicted values to the ground truth or to the actual values. That is when we'll be able to tell, how well our model is performing. So here we have a table of the actual values against the predicted values from the model. So basically what I did was to run the first model, which was not transformed, and then compare it to the actual value. And then I also run the log transformed model and then determined how much it improved after it was transformed. And here in the highlighted columns, notice that prior to transformation, our model was predicting, it was off the actual, these are the actual values. So the predicted values were off by 21% in winter. It was off by 6 in spring, summer 15, and then also fall 15. But when it's transformed, we notice that it is improved significantly. Here, notice that our predicted for winter of 2018 is off the actual by 14%. And then this spring remains the same. However, for summer and fall, notice how much it is improved. So it is very evident that 3% increase, or just transforming the target variable, was very, very useful in improving the performance of this model. And so in conclusion, I would say that population size, household income, listed prices, seasons of the year are all very good predictors of days on market. Individually, as you would have seen when I started presenting, most of these variables by themselves didn't have a very strong relationship, but brought together, they were able to perform very well in the model. And also, the performance we see here might not necessarily be the same for each state. As you can see, this is being predicted only for Maryland. And as I mentioned earlier, I'm only doing this because creating a model for the whole country doesn't make sense, because we have different location characteristics that cannot be applied to the whole country. However, if we limit it to state by state, it reduces the influence on our model. Now, lessons learned: if patterns cannot be identified at higher levels of detail, then always consider aggregating down to a single value that is less granular, like I did for this data, predicting for seasons. And also, the moment you aggregate down, that means it reduces the size of your data. And so I realized that it's always good to have a much bigger data set when you have intentions to reduce or to aggregate down. Otherwise, you wouldn't have enough data points for your model. Here are my references, and if you have any questions, please let me know. If you have any comments, I would definitely appreciate it. Thanks to all of you for all your past comments. It's been very useful in being able to come up with a final model that is able to predict very close to what do you call it, the actuals. Thank you once again.